Look up tonight. Really look. There are roughly 1 septillion stars in the observable universe. That's a 1 followed by 24 zeros. Each one of them burning, fusing hydrogen into helium, pouring out energy in every direction at a rate that dwarfs anything humans have ever built or imagined. Some of the largest stars release more energy every single second than our sun produces in an entire year. And they've been doing this for billions of years. In every direction, without stopping. So why is it dark? Not dim, not slightly underwhelming. Dark. Genuinely, profoundly, almost completely dark. You can cover the full moon with your thumb. You can block every visible star in the night sky with a piece of paper held at arm's length. The darkness between those points of light isn't just empty space waiting to be filled. It's something the universe chose. And the reason it chose it tells you more about the history of everything than almost any other observation you could make standing in your backyard. The puzzle has a name, Olbers paradox, named after Heinrich Wilhelm Olbers, a German astronomer who laid the problem out in 1823 with such clarity that it's been attached to his name ever since, even though he wasn't actually the first person to notice it. Thomas Digges raised something similar in the 16th century. Johannes Kepler worried about it in the early 1600s. Edmund Halley wrote about it in the early 1700s. The puzzle kept resurfacing because nobody could shake it, and nobody could solve it. The logic is so simple it's almost insulting. If the universe stretches in every direction and fills with stars, which it does, then every line of sight from your eye should eventually terminate on the surface of a star. Think of standing in a forest, dense enough that no matter which direction you look, a tree trunk blocks your view before you see the horizon. Stars are the trees. If there are enough of them, and they extend far enough, the entire sky should be as bright as the surface of a star. Not just scattered points of light. One continuous blazing wall of light in every direction, day and night, without relief. The math actually confirms the nightmare. Double the distance to a star, and its apparent brightness drops to 1/4. Brightness falls with the square of distance. But double the distance, and the volume of space at that distance increases with the square of the distance too. More stars. The two effects cancel out exactly. Every shell of stars at increasing distances contributes the same total light to the sky as every closer shell. Add infinite shells together, and you get infinite brightness. Olbers' math was correct. His logic was sound. The sky should be on fire. It isn't. For most of the 19th century, the obvious guess was absorption. Dust and gas between the stars block the light before it reaches us. Clean solution. Simple. Wrong. Here's why. If interstellar dust absorbs light, the dust heats up. Given enough time, and an infinite universe has infinite time, that heated dust reaches thermal equilibrium with its surroundings and radiates as much energy as it absorbs. It glows. You haven't removed the light, you've just delayed it by a few million years and changed its address. An infinite universe with infinite time would heat everything up to the same temperature as a stellar surface, dust included. The absorption explanation doesn't solve the paradox, it just moves it down the road. The real answer required something nobody in the 19th century was ready to accept. The universe doesn't have infinite time. It has a beginning. 13.8 billion years ago, everything that exists was compressed into a state of inconceivably high density and temperature. Space and time themselves began. Physics as we know it started. And from that moment, light has been traveling outward in every direction at 300,000 kilometers per second. Fast. Unimaginably fast by any human standard. But the universe is bigger, much bigger. Because the universe has existed for only 13.8 billion years, we can only see light that has had time to reach us, not the light from every star that exists, or has ever existed, anywhere. Only the light from stars close enough that their photons have already made the journey. This creates the observable universe, a sphere of roughly 46 billion light-years in radius, not because space ends there, but because light beyond that boundary hasn't arrived yet. It's still traveling. We're sitting here waiting for mail from addresses that existed 13 billion years ago, and the Postal Service only moves at the speed of light. That finite age cuts off Olber's infinite sum before it reaches infinity. The math no longer produces infinite brightness. It produces a very large, but very finite number. And that number is small enough that the sky stays dark. But here's where it gets stranger. Even that finite age explanation isn't quite enough on its own. Run the numbers for all the stars within our observable universe, and you'd still expect more light than we actually see. Something else must be draining it away. That something is expansion. Edwin Hubble figured it out in the late 1920s, measuring the light from distant galaxies using the world's largest telescope at the time, perched on Mount Wilson in California. Every galaxy he looked at was moving away, and the farther away it was, the faster it was receding. This wasn't galaxies flying through space like bullets. Space itself was stretching, carrying galaxies apart the way dots painted on a balloon separate as you inflate it. Run that expansion backward, and everything converges. About 13.8 billion years ago, all of space was compressed into an extraordinarily hot, dense state. What we call the Big Bang wasn't an explosion happening at a point. It was the beginning of space itself, everywhere at once, followed by relentless expansion ever since. That expansion does something devastating to light. As a photon travels across the universe, the space it's moving through stretches. That stretching increases the photon's wavelength. A longer wavelength means lower frequency, and lower frequency means less energy. The light doesn't disappear, but it gets stretched, weakened, shifted toward the red end of the spectrum, and then beyond it, into infrared, then into microwave wavelengths, invisible to human eyes entirely. Ancient light from the earliest galaxies doesn't arrive as bright, visible light. It arrives as a faint whisper of microwave radiation, too long in wavelength and too thin in energy for our eyes to register at all. The sky isn't dark because that light failed to arrive. It's dark because when it arrived, it had been stretched past the range our biology can detect. There's a third factor, quieter than the others but worth sitting with for a moment. Stars are enormous by any human scale. The Sun has a diameter of about 1.4 million kilometers. You could fit more than 1 million Earths inside it. But the nearest star, beyond our own, Proxima Centauri, sits about 4 light-years away, roughly 40 trillion kilometers. On a scale where the Sun shrinks to the size of a marble, Proxima Centauri is another marble, sitting approximately 300 kilometers away. And between them, nothing. This ratio, the physical size of stars compared to the distances separating them, means that even with a septillion stars in the observable universe, the fraction of the sky actually covered by stellar surfaces is absurdly small, far less than 1 part in a trillion. Most lines of sight from your eye don't hit a star. They pass straight through the dark between them, all the way to the edge of the observable universe, where the light that finally arrives has been stretched into invisibility by billions of years of cosmic expansion. Space is almost entirely empty, even when you count every star that has ever formed. Now here's the part that most explanations leave out, and it's the part that should genuinely unsettle you. In the 1960s, 2 radio astronomers at Bell Labs in New Jersey were trying to eliminate a persistent noise from their antenna. Arno Penzias and Robert Wilson kept picking up a faint, uniform hiss of microwave radiation coming from every direction simultaneously. regardless of where they pointed the dish, regardless of the season. They cleaned the antenna, they removed pigeon droppings. The noise didn't go away. It was the oldest light in the universe. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was a hot, dense plasma, opaque, like a fog too thick for light to penetrate. Once neutral atoms formed, the universe became transparent for the first time, and the light that had been trapped in that plasma flooded out in every direction. Billions of years of cosmic expansion stretched that light from what was once similar to the glow of a stellar surface, thousands of degrees, down to just 2.7 degrees above absolute zero, far into the microwave range. Penzias and Wilson had accidentally detected the afterglow of creation, the cosmic microwave background radiation. And it fills the entire sky, uniformly, in every direction, right now. In a very real sense, Olbers was right. The sky is glowing. Every single direction blazes with ancient light. It's just been stretched so far beyond the visible spectrum by expansion that human eyes can't see any of it. If you could somehow perceive microwaves the way you perceive visible light, the entire night sky would glow with a soft, perfectly uniform, faint light. The heat of the Big Bang, still detectable nearly 14 billion years later. Penzias and Wilson received the Nobel Prize in Physics in 1978 for stumbling onto one of the most profound discoveries in the history of science while trying to debug a radio antenna. There's something philosophically jarring buried in all of this that rarely gets mentioned directly. The darkness of the sky depends on the universe being young enough that most of the light that exists hasn't reached us yet. That's a genuinely strange thing to say. The observable universe contains something on the order of 2 trillion galaxies, each containing hundreds of billions of stars, pouring out energy continuously. And we live in the dark because we haven't been waiting long enough. The universe is generous with its light. It's stingy with its time. And because light travels at a finite speed, when you look at a star, you're not seeing it as it exists right now. You're seeing it as it was when the light left. The nearest star beyond our sun shows you light that departed 4.24 years ago. Polaris, the North Star, sits roughly 433 light-years away. That light left before the telescope was invented, before Shakespeare, during the early decades of the Renaissance. The Andromeda Galaxy, the nearest major galaxy, shows you a smudge of light that began its journey 2.5 million years ago, long before anything recognizable as modern humans walked the Earth. Every point of light in the night sky is a message from a different moment in the past. The sky is a patchwork of different eras, overlapping, layered, compressed into one view the moment you look up. And the darkness between those points represents the future, light that hasn't arrived yet. Light from stars so far away that even though it's been traveling for billions of years, the distance is still winning. The long-term future of this darkness deserves attention because it's stranger than the present. Right now, we live in what astronomers call the stelliferous era, the age of stars. Galaxies are actively forming new stars, burning hydrogen, producing light. Our own galaxy, the Milky Way, forms roughly 1 to 2 solar masses of new stars every year. The night sky we see tonight, dark as it is, still contains countless active burning suns. But the Milky Way's gas supply, the raw material for new stars, won't last forever. Estimates suggest meaningful star formation will continue for perhaps another 100 trillion years. After that, no new stars. The existing ones will age and die. White dwarfs will cool over unimaginable timescales, fading from dim red to complete darkness, becoming what physicists call black dwarfs. Though none actually exist yet in our universe, because the cooling process takes longer than the current age of everything. Expansion will eventually carry all other galaxies beyond our cosmological event horizon. Their light, no matter how long we wait, will never reach us again. One by one, galaxies will vanish from our observable sky. By the far future, an intelligent civilization looking up from within what remains of the Milky Way would see only a handful of dying stars in their own isolated galactic remnant. No other galaxies visible, no cosmic microwave background detectable. It will have been stretched beyond any possible detection. No evidence that other galaxies ever existed at all. They would have no way to reconstruct the history of the universe the way we can today. This is one of the more quietly disturbing implications of cosmic expansion. We may exist during a cosmically brief window when the evidence for the universe's true history is still visible. Future civilizations, far enough into the future, might look up and conclude they live in a static, isolated, unremarkable system with nothing much beyond their own galaxy. The evidence for the Big Bang, for expansion, for the true scale of the cosmos would have literally moved beyond the horizon. We happen to be looking up at exactly the right time. The reason most of this stays hidden from ordinary experience involves something basic about human biology. Eyes adapted for daylight work through cone cells, sensitive to color and detail, requiring reasonable amounts of light. At night, the eye shifts to rod cells, far more sensitive to low light levels, but unable to distinguish color and providing much lower resolution. Under ideal dark conditions, the human eye can detect a single photon in the laboratory. But individual faint stars deliver photons too sparsely for the visual system to distinguish from random noise. The signal doesn't accumulate fast enough. Countless galaxies exist in every direction, each contributing a trickle of light completely below the detection threshold of unaided human vision. This is why the Hubble Space Telescope's deep field images remain so startling. Astronomers pointed Hubble at a patch of sky that appeared completely empty, a region small enough to be covered by a grain of sand held at arm's length, and left the detector accumulating light for hours across multiple observing sessions. What emerged was staggering. That apparently empty patch contained thousands of individual galaxies, each one containing billions of stars, all invisible to the naked eye and invisible to a single short exposure, revealed only when the photons were given enough time to pile up. The universe isn't dark because there's nothing there. A significant fraction of the darkness you see with the naked eye is darkness only because human vision has limits. The light exists. Your eyes just can't collect enough of it fast enough to register. One more layer sits underneath everything we've covered, and it pushes the strangeness into territory most astronomy explainers skip entirely. Ordinary matter, the atoms that make up stars, planets, gas clouds, accounts for only about 5% of the universe's total energy content. Roughly 27% of the universe's mass energy content consists of dark matter, something that doesn't emit, absorb, or reflect light in any form we can detect, interacting with ordinary matter only through gravity. We know it exists because galaxies rotate in ways that can't be explained by their visible mass alone. Because gravitational lensing around galaxy clusters bends light more than the visible matter could account for. Because the large-scale structure of cosmic filaments wouldn't have formed without it. The remaining 68% consists of dark energy, something driving the accelerating expansion of space itself, discovered in the late 1990s when two independent teams studying distant supernova explosions expected to find the expansion slowing down from gravity, and instead found it speeding up. Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011 for that discovery. Neither dark matter nor dark energy contributes any light to the sky. Not because they absorb light, but because they simply don't participate in the processes that produce light in the first place. The overwhelming majority of what the universe actually contains, by mass, by energy, by presence, is permanently invisible. Not hidden, not waiting to be found. Invisible by nature. 95% of everything that exists would never show up in the night sky, regardless of the universe's age, regardless of its expansion, regardless of any other factor. The night sky doesn't just look dark because of physics and geometry. It looks dark because most of existence was never going to contribute to it anyway. This leaves a final observation that deserves to sit quietly for a moment before moving on. The specific conditions responsible for the darkness of the sky are the same conditions responsible for the existence of life. If Ulber's scenario were real, if the sky blazed uniformly with the brightness of a stellar surface, the temperature everywhere in the universe would be thousands of degrees. No liquid water, no stable molecular chemistry, no biology of any kind recognizable to us. The darkness isn't just aesthetically interesting. It's a prerequisite for existence. A universe old enough, cold enough, and sparse enough to keep the sky dark is a universe stable enough to produce stars that last for billions of years, planets at appropriate distances, conditions that remain roughly constant for long enough for chemistry to become biology. The same finite age that limits our view of the cosmos is what gives life the time it needs to evolve. The darkness above you every clear night isn't an absence. It's evidence of a universe with a beginning, of space that stretches and cools, of distances so vast they defeat even the prodigious output of a septillion burning suns, and of a brief moment in cosmic history when all of that evidence is still visible, still measurable, still telling its story to anyone patient enough to look up and ask why the sky looks the way it does. Here's something nobody tells you about starlight. Every photon that reaches your eye tonight has survived an obstacle course that would have destroyed it 1,000 times over if the universe were even slightly different. It had to escape the turbulent outer layers of its star. It had to travel across millions or billions of light years without hitting anything, a journey through a medium so thin that a cubic centimeter of interstellar space contains, on average, about one single atom. It had to survive billions of years of cosmic expansion that stretched its wavelength, weakened its energy, and shifted its color away from the frequencies your eye can actually detect. And then, after all of that, it had to happen to arrive at exactly the right patch of space where a small blue planet had assembled retinas capable of registering it. Most photons don't make it, not because the universe stops them, because the universe is so vast that even traveling at 300,000 kilometers per second for 13 billion years, most light simply hasn't reached anything yet. The scale problem is worth sitting with longer than most explanations allow. When astronomers say the observable universe contains around 2 trillion galaxies, that number has a tendency to wash over people without landing. 2 trillion. That's 2 followed by 12 zeros. Each of those galaxies contains somewhere between 10 billion and 1 trillion stars. The Milky Way alone holds an estimated 200 to 400 billion stars, each one a nuclear furnace, burning at temperatures of millions of degrees at its core, pouring energy outward in every direction, continuously. Take our own sun as a benchmark. Every second, the sun converts about 4 million metric tons of mass directly into energy through nuclear fusion. Every second. That energy radiates outward in all directions across space. At the distance of Earth, about 150 million kilometers, only an infinitesimal fraction of that energy reaches us. The rest spreads across the rest of the sphere of space surrounding the sun, growing thinner with every kilometer it travels. Now multiply that output by 400 billion for our galaxy alone. Then multiply by 2 trillion for all the galaxies in the observable universe. The total luminosity of the observable universe is a number so large that writing it out requires notation that makes ordinary large numbers look trivial. And yet, dark. The inverse square law deserves its own moment of attention because it's doing more work in this story than it usually gets credit for. When light travels outward from a source, it spreads across an ever-expanding sphere. The area of a sphere increases with the square of the radius. Double the distance, and the same amount of light now covers 4 times the area, making it appear 1/4 as bright at any given point. This is why distant stars look faint even when their actual energy output dwarfs our Sun. Rigel, one of the brightest stars visible in the constellation Orion, produces roughly 120,000 times more energy than our Sun. But Rigel sits about 860 light-years away. By the time its light crosses that distance and arrives at Earth, the inverse square law has diluted its apparent brightness down to something a careful naked-eye observer can just about see on a clear night. Comparable in apparent brightness to dozens of much dimmer but much closer stars. Now push that thinking outward to truly intergalactic distances. A star 10 million light-years away would need to outshine our Sun by a factor of about 44 quadrillion just to appear as bright as the faintest star visible to the naked eye. No star achieves that. No collection of stars in a single galaxy comes close at that distance. Distance wins. It always wins. The 1990s produced a discovery that changed everything about the darkness of the sky in ways that still haven't fully filtered into popular understanding. 2 independent research teams, one led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, the other led by Brian Schmidt and Adam Rees at Australian National University and Harvard, spent the early 90s meticulously measuring the brightness of Type 1a supernovae in distant galaxies. Type 1a supernovae are exceptionally useful as what astronomers call standard candles. They result from a remarkably consistent physical process, a white dwarf accreting mass from a companion star until it reaches a critical threshold and detonates, producing a peak brightness that can be calibrated with reasonable precision. By comparing how bright these supernovae appeared from Earth against how bright they should have been at their measured distances, the teams expected to find that the expansion of the universe was slowing down. Gravity pulls matter together. The external from the Big Bang should have been decelerating over billions of years. Instead, they found the opposite. Distant supernovae were dimmer than they should have been, not by a little. The universe wasn't decelerating, it was accelerating. Something was pushing space apart at an increasing rate, overcoming the gravitational pull of all the matter in the universe. That something is what physicists call dark energy. It comprises roughly 68% of the total energy content of the universe and remains, 2.5 decades after its discovery, almost completely mysterious. We don't know what it is. We know it exists because of what it does. It drives cosmic expansion, and it does so with increasing intensity over time. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for that discovery. The implications for the darkness of the sky are significant and strange. If dark energy continues accelerating cosmic expansion, and every observation suggests it will, the universe will grow darker faster than it would have otherwise. Galaxies that are currently retreating from us will eventually cross what's called the cosmological event horizon. Beyond that boundary, their recession speed exceeds the speed of light, not because the galaxies themselves move faster than light, but because the space between us and them expands faster than light can cross it. Once a galaxy crosses that horizon, its light can never reach us again. Not eventually. Never. The sky is dark now. It will be darker in 1 trillion years, and darker still in 10 trillion. The cosmic microwave background deserves more time than most treatments give it, because what it represents is genuinely staggering when you think it through carefully. When the universe was about 380,000 years old, something happened that had never happened before and would never happen quite the same way again. The universe cooled below roughly 3,000 degrees Kelvin. At that temperature, free electrons could combine with protons to form neutral hydrogen atoms, without immediately being blasted apart again by energetic photons. The plasma that had filled all of space since the Big Bang, opaque, glowing, impenetrable to light the way the interior of a star is impenetrable, suddenly became transparent. Every photon that had been trapped in that plasma, scattering endlessly off free electrons, suddenly found itself free to travel in a straight line. The universe went from opaque to transparent in a cosmological eye blink. And all that light flooded outward in every direction simultaneously, from every point in space at once. That light still exists. It's been traveling for 13.8 billion years. It's been stretched by the expansion of the universe from a wavelength corresponding to several thousand degrees Kelvin down to a temperature of just 2.725 degrees above absolute zero, the coldest temperature in the observable universe. And also, one of the most precisely measured numbers in all of science. The Wilkinson Microwave Anisotropy Probe, launched in 2001, and the Planck satellite, launched in 2009, mapped the tiny temperature variations in this background radiation. Variations of just a few parts in 100,000, with extraordinary precision. Those tiny fluctuations are the seeds of everything. The slightly denser regions of that ancient light correspond to slightly denser regions of matter. Over billions of years, gravity amplified those tiny differences. Dense regions attracted more matter. More matter attracted more matter still. Eventually, those regions collapsed into the first stars, the first galaxies, the vast filaments and voids of the cosmic web visible today. The darkness of the sky and the existence of everything in it trace back to those infinitesimal wrinkles in a glow that's been traveling since before the first star ever lit. Here's the question that follows naturally from everything above and rarely gets asked directly. Could a civilization elsewhere in the universe, at a different time in cosmic history, even figure out the answers we've worked out? The answer depends entirely on when they're looking. We exist at a cosmically brief moment, roughly 13.8 billion years after the Big Bang, when the evidence for the universe's true nature is still accessible. The cosmic microwave background is still detectable. Distant galaxies are still visible, their recession velocities still measurable through redshift. The large-scale structure of cosmic filaments still reveals the gravitational fingerprints of dark matter. The age and expansion history of the universe can still be reconstructed from multiple independent lines of evidence. Move the clock forward by 100 billion years, and the picture changes dramatically. Dark energy will have carried most currently visible galaxies beyond the cosmological event horizon. No redshift measurements possible. The cosmic microwave background will have been stretched to wavelengths so long and energy so thin that no conceivable instrument could detect it. The large-scale structure observations that reveal dark matter's influence will be inaccessible. A civilization arising 100 billion years from now, in whatever isolated galactic remnant remains observable to them, would look up and see only a small number of aging stars in their own galaxy. Nothing beyond. No evidence of expansion, no evidence of the Big Bang. No way to detect dark energy or dark matter through cosmic scale observations. They would almost certainly conclude they lived in a static, small, isolated universe with no particular history. They would be completely wrong, and they would have no way to know it. This means that our current understanding of the universe, the Big Bang, cosmic expansion, the cosmic microwave background, dark matter, dark energy, the large-scale structure of the cosmos, depends critically on having arisen at exactly this point in cosmic time, while the evidence is still here to read. Earlier would have been fine. Much later, and the evidence disappears behind the expanding horizon, and the universe simply stops telling its own story to any observer inside it. The structure of the universe on the largest scales adds another layer to why the sky looks the way it does. Galaxies don't scatter randomly through space. They organize into an intricate three-dimensional network that astronomers call the cosmic web. Filaments of galaxies stretch across hundreds of millions of light years, intersecting at dense nodes called galaxy clusters. Between the filaments lie enormous voids, regions of space that appear nearly empty of galaxies, stretching for hundreds of millions of light years in every direction. The Bootes void, discovered in 1981 by Robert Kirshner and colleagues during a survey of galaxy redshifts, extends roughly 330 million light-years across. That's a region of space large enough to contain thousands of galaxies based on average cosmic density, and it appears to contain only about 60. Standing inside such a void, if any civilization happened to evolve there, the night sky would appear even emptier than ours. Fewer galaxies visible, fainter and more widely separated points of light. A sky closer to complete blackness than what we see from our relatively well-populated corner of the Laniakea supercluster. Conversely, a civilization in the dense core of a massive globular cluster, where stars pack together far more tightly than anywhere in our galactic neighborhood, would look up at a sky genuinely bright enough on the darkest nights to cast visible shadows. Dozens of stars, at distances comparable to our nearest stellar neighbors, each one visible as a distinct bright point rather than the single bright dot of Proxima Centauri that our best telescopes can barely resolve. Not the wall of fire Olbers imagined, but something far more luminous than our experience. The darkness isn't uniform across the universe. It varies with location, with local stellar density, with proximity to voids and filaments. But the fundamental physics remains constant everywhere. Finite age, expanding space, inverse square law. Those constraints apply equally to every civilization in every corner of the observable universe. No local variation in stellar density overcomes them. The electromagnetic spectrum complicates the darkness story in one final direction that deserves careful attention. When we say the sky is dark, we mean it's dark to human eyes. Human eyes detect a narrow sliver of the electromagnetic spectrum, visible light, with wavelengths ranging from roughly 400 to 700 nanometers. Outside that range, we're blind without instruments. But the universe broadcasts across the entire spectrum, all the time, from every direction. Radio waves from pulsars and active galactic nuclei, infrared radiation from warm gas clouds and newly forming stars, ultraviolet light from hot, young, massive stars, X-rays from matter falling into black holes and colliding galaxy clusters, gamma rays from the most violent events in the cosmos, neutron star mergers, gamma-ray bursts, supernovae. The night sky, mapped in X-rays, glows with dozens of bright sources. Mapped in radio waves, it blazes with structure in invisible light. Mapped in gamma rays, it erupts occasionally with bursts so energetic that a single event, a gamma-ray burst detected on October 9, 2022, and immediately nicknamed the Boat for brightest of all time, briefly outshone in gamma rays everything else in the observable universe combined. That burst originated about 2 billion light-years away. It ionized Earth's upper atmosphere from that distance. The sky is dark only because of the specific biology of human vision. In every wavelength simultaneously, it seethes with radiation from every direction. One more physical reality about light loss in transit that rarely appears in popular discussions. Photon energy loss from cosmic expansion isn't just a color shift. It's a genuine energy reduction with thermodynamic consequences. A photon's energy relates directly to its frequency through Planck's equation, E equals h times f, where E is energy, h is Planck's constant, and f is frequency. Stretch the wavelength, which is what cosmic expansion does to every photon in transit, and the frequency drops. Drop the frequency, and the energy drops proportionally. Ancient light from the earliest galaxies doesn't just arrive in a different color, it arrives carrying less energy per photon than it had when emitted. This means that even if we could somehow collect every photon from every star in the observable universe, even accounting for all of them that haven't arrived yet, the total energy delivered would still be finite and manageable. Expansion doesn't just limit how many stars we can see, it actively drains the energy from the light those stars do send us. Every year that passes, every additional megaparsec of cosmic expansion between a distant galaxy and Earth costs those photons a fraction of the energy they started with. The universe taxes its own light, and the tax accumulates over billions of years. There's a version of this story that gets told through numbers alone, and it's worth doing carefully once because the numbers are more surprising than the prose usually conveys. The total luminosity of the observable universe, adding up the energy output of every star in every galaxy we can observe, runs to approximately 5 × 10⁴ watts. That's 5 followed by 44 zeros. An incomprehensible figure. But spread that energy across the surface area of a sphere with a radius of 46 billion light-years, the radius of the observable universe, and the energy flux at any given point drops to something extraordinarily thin. A tiny fraction of the energy hitting Earth from the Sun. And that's before accounting for the fact that much of that light has been redshifted out of the visible spectrum, that the universe's finite age means light from the most distant stars hasn't arrived yet, and that most of the universe's energy exists as dark energy and dark matter that produce no light at all. The math works out. The sky stays dark, not because the universe lacks light sources, because the universe is too big, too old in the wrong direction, and too actively expanding for all that light to arrive, intact and visible, at any given point inside it. Here's what makes Olber's paradox unusual among scientific puzzles. It took 300 years and essentially the entire apparatus of modern cosmology to resolve a question any child can ask on the first clear night they spend outside. Thomas Digges in the 1500s, Kepler in 1610, Halley in the 1700s, Olbers in 1823. A question asked repeatedly by serious minds without resolution. It required Edwin Hubble's measurement of cosmic expansion in 1929. It required the accidental detection of the cosmic microwave background by Penzias and Wilson in 1965. It required the discovery of dark energy by Perlmutter, Schmidt, and Rees in 1998. It required decades of precision mapping of the cosmic microwave background by COBE, WMAP, and Planck. It required a complete reconceptualization of what the universe fundamentally is. Not a static, eternal stage, but a dynamic entity with a beginning, an age, and an ongoing expansion that stretches and dims every photon in transit. A question about absence, about why something isn't there, turned out to require understanding more about the universe than most questions about what is there. The darkness between the stars isn't empty. It's the answer to every question about where the light went. It carries the age of the universe, the speed of expansion, the thermodynamic history of space from 3000 Kelvin to 2.7 Kelvin, and the geometric reality of distances so vast that even septillions of burning stars can't fill them with light. Every time you look up at a dark patch between two visible stars, you're looking at the solution to a 300-year-old mystery. You just need to know what you're seeing. There's a number that deserves more attention than it usually gets in conversations about cosmic darkness. The photon. Not the concept, the actual particle. Right now, every square centimeter of your body gets hit by roughly 1,000 photons of cosmic microwave background radiation every single second. Not occasionally, not in bursts, continuously, from every direction simultaneously, at a rate of 1,000 per square centimeter per second. They pass through you without interacting with anything in your body because their wavelength is roughly 2 millimeters, far too long to be absorbed by biological molecules. They go straight through walls, through floors, through the planet itself. They have been doing this since about 380,000 years after the Big Bang. Every point in space, everywhere in the observable universe, gets hit by the same relentless rain of ancient photons. The sky is dark to your eyes. To a microwave detector, the sky glows uniformly in every direction, with more photons than you could count in 1,000 lifetimes. The darkness is a feature of your biology, not of the universe. The redshift story has one more chapter that most explanations stop short of fully exploring. When Edwin Hubble measured the recession velocities of distant galaxies in the 1920s, he established what became known as Hubble's law. The recession velocity of a galaxy scales proportionally with its distance. The proportionality constant, now called the Hubble constant, tells you how fast space expands per unit of distance. Current measurements place it at roughly 67 to 73 kilometers per second per megaparsec, depending on which measurement technique you use. That tension between the two values, known as the Hubble tension, remains one of the most actively debated problems in modern cosmology, with researchers genuinely uncertain whether it reflects systematic measurement errors or new physics beyond our current understanding. But here's the piece that connects directly to darkness. The Hubble constant tells you something specific about where the cosmological event horizon sits, the boundary beyond which recession speeds exceed the speed of light. That boundary currently sits at roughly 16 billion light-years from Earth. Any galaxy beyond 16 billion light-years recedes from us faster than light can travel, meaning its photons are losing ground against the expansion of space between us. Those photons will never arrive. Not because anything stops them from traveling, because the space they need to cross keeps growing faster than they can cross it. The observable universe extends to about 46 billion light-years. That larger figure reflects the fact that space has been expanding the entire time the light from those distant regions was traveling toward us, so the sources are now much farther away than the distance light has traveled. Between 16 billion and 46 billion light-years sit galaxies whose ancient light has already reached us, but whose future light never will. We can see their past. We will never see their present, or anything that happens to them from this point forward. Every galaxy beyond 16 billion light-years has already sent its last photon toward Earth that will ever arrive. The rest are gone. Not traveling, gone. Gravitational lensing adds a wrinkle to the darkness question that cuts in an unexpected direction. Massive objects, galaxy clusters, individual massive galaxies, even concentrations of dark matter, bend the paths of photons passing nearby. This gravitational lensing effect can both magnify and redirect light from sources that would otherwise be too faint or too small to detect. In some cases, gravitational lensing produces multiple images of the same distant galaxy, arranged in arcs around a foreground cluster, or, in the most geometrically perfect cases, a complete ring, an Einstein ring, first predicted by Einstein in 1936 and first observed in 1988 through radio telescopes. What lensing means for cosmic darkness is subtle but real. Some fraction of the light that would otherwise miss Earth gets redirected toward us by intervening mass. We see gravitationally focused images of objects that would remain invisible if space between us were perfectly flat and empty. The James Webb Space Telescope routinely exploits this effect deliberately, pointing at massive galaxy clusters and using them as cosmic magnifying glasses to examine galaxies behind them that Webb's mirrors couldn't otherwise resolve. But lensing also means the sky isn't quite as simple as a collection of straight lines from sources to observers. Every photon path curves through the gravitational landscape of the universe. Some light that originated heading in other directions arrives at Earth instead. Some light heading toward Earth gets bent away. The net effect on total sky brightness is small, but it means the darkness you see overhead isn't a simple geometric result of sources and distances. It's filtered through the warped space-time geometry of every massive object between us and every source of light. The question of whether the universe is finite or infinite deserves direct engagement because it affects how the darkness paradox gets resolved at the deepest level. Based on extremely precise measurements of the cosmic microwave background, particularly the angular scale of temperature fluctuations, which depends sensitively on the overall geometry of space, the universe appears spatially flat to within our current measurement precision. A flat universe, in the technical sense, means that parallel lines remain parallel indefinitely, and the angles of a triangle sum to exactly 180 degrees across all scales. This is the geometry Euclid described, as opposed to the curved geometry of a sphere or a saddle. A perfectly flat universe could, in principle, be infinite in spatial extent, extending forever in every direction, containing infinitely more galaxies and stars beyond what we can observe. Or it could be finite but very large, perhaps with a topology that wraps around on itself at scales vastly larger than our observable horizon. Current observations can't distinguish between these possibilities. The universe is at minimum vastly larger than the portion we can see. Here's the critical point. Even if the universe genuinely extends infinitely in every direction, containing infinite stars beyond our cosmological horizon, the paradox doesn't return. Those infinite stars have no access to our observable sky. Their light hasn't reached us and, for the most distant of them, due to expansion, never will. The observable universe remains finite, regardless of what lies beyond it. The darkness doesn't depend on whether infinity exists out there. It depends on the boundary between what can reach us and what can't. Infinity beyond the horizon changes nothing about the view from inside it. There's a thermal history to the universe that connects the darkness story to chemistry and biology in ways that rarely get acknowledged. After the Big Bang, the universe passed through a sequence of temperature regimes that successively enabled and disabled different physical processes. For the first few minutes, temperatures exceeded tens of millions of degrees, hot enough for nuclear fusion to occur spontaneously throughout all of space. During those first few minutes, roughly 25% of all ordinary matter fused into helium, with smaller amounts of deuterium, helium-3, and lithium also forming. The rest remained as hydrogen. This process, called Big Bang nucleosynthesis, established the basic elemental composition of the universe before a single star ever formed. The ratio of hydrogen to helium observed today in the oldest, least chemically processed stars matches the predictions of Big Bang nucleosynthesis with extraordinary precision, providing independent confirmation of the universe's thermal history. As the universe expanded and cooled below fusion temperatures, nuclear burning stopped everywhere simultaneously. The universe became a dark gas of hydrogen and helium, too cool for stars, too hot for atoms. For the next roughly 380,000 years, the universe existed in a state of glowing plasma, hot enough to be opaque, the photons unable to travel freely. Then came recombination. The transition from opacity to transparency we covered earlier. The universe went dark, in the sense that the primordial plasma glow ended. Not permanently dark. Stars would eventually form. But for the period between recombination and the ignition of the first stars, a span of perhaps 200 million years, the universe contained no sources of visible light. Astronomers call this period the Cosmic Dark Ages, and it was precisely as the name implies, a universe of hydrogen and helium gas, cooling, with no stars, no galaxies, no light beyond the fading cosmic microwave background, stretching into longer and longer wavelengths. The Cosmic Dark Ages ended when the first stars ignited. Those first stars, called Population 3 stars, were fundamentally different from anything that exists today. Formed from pure hydrogen and helium with no heavier elements at all, they were likely far more massive than typical present-day stars, possibly hundreds of times more massive than our Sun. Their lifetimes were correspondingly brief, just a few million years before exploding as supernovae, seeding the surrounding gas with the first heavy elements: carbon, oxygen, nitrogen, iron, silicon. Those expelled elements made the next generation of stars slightly less extreme, and those stars made more heavy elements, and so on, generation by generation, until enough carbon and silicon and iron accumulated in the universe to make planets, and enough complex chemistry to make life. Every atom in your body heavier than hydrogen or helium was forged in the interior of a star that died before the sun formed. The darkness between stars isn't just empty space, it's the residue of every stellar generation that had to live and die to build the elements that make life possible. The practical experience of darkness, what it actually feels like to stand under a truly dark sky, has become increasingly rare in a way that deserves direct acknowledgement. In 1994, a major earthquake struck Los Angeles. Power went out across the city. For the first time in decades, residents of one of the largest cities in North America looked up and saw the Milky Way. Emergency call centers received reports from confused residents asking about a strange silver cloud overhead. Some people had never seen it before. That story, and versions of it appear in multiple accounts from that night, captures something specific about what light pollution has done to human experience of the sky. Studies by Fabio Falchi and colleagues, published in Science Advances in 2016, found that roughly 83% of the world's population and 99% of the population of the United States and Europe lives under light-polluted skies. About 1/3 of humanity can no longer see the Milky Way from where they live, regardless of conditions. The irony is precise. We live in the era of greatest scientific understanding of cosmic darkness. We know why the sky is dark to a degree no civilization in history could have understood. And simultaneously, the largest fraction of humans in recorded history can't actually experience the darkness we've spent so long learning to explain. The sky above different wavelengths tells radically different stories, and mapping those stories reveals how much of the universe's activity happens completely outside human perception. In radio wavelengths, the sky blazes with synchrotron radiation from relativistic electrons spiraling in magnetic fields, jets from active galactic nuclei, the remnants of ancient supernovae, the diffuse radio emission of the Milky Way's magnetic field. The brightest radio source in the sky after the Sun is Cassiopeia A, the remnant of a star that exploded roughly 300 years ago at a distance of about 11,000 light-years. It doesn't appear in visible light as anything particularly notable. In X-ray wavelengths, the sky reveals a universe in violent motion. The Chandra X-ray Observatory, launched in 1999, has mapped thousands of X-ray sources. Neutron stars spinning hundreds of times per second, black holes tearing apart companion stars and accreting their material. Galaxy clusters with intra-cluster gas heated to tens of millions of degrees. Active galactic nuclei powered by supermassive black holes consuming matter at prodigious rates. In infrared, the sky becomes transparent to dust in ways visible light can't manage. The center of the Milky Way, completely hidden behind thick dust clouds in visible light, glows brilliantly in infrared. The James Webb Space Telescope operates primarily in the near and mid-infrared for exactly this reason. The most distant galaxies, whose light has been redshifted far out of the visible range, become accessible only there. Webb's first deep-field image, released in July 2022, revealed thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Some of them seen as they appeared just a few 100 million years after the Big Bang. The visible darkness is one layer of a multi-layered electromagnetic reality. Human eyes reveal one narrow slice of it. The universe conducts its business across all the others, simultaneously, continuously, without acknowledgement. The violence hidden inside apparent darkness is worth dwelling on. Gamma-ray bursts are the most energetic events in the observable universe since the Big Bang itself. They occur in two varieties: long bursts lasting more than 2 seconds, associated with the collapse of massive rotating stars into black holes, and short bursts lasting less than 2 seconds, now confirmed through gravitational wave observations to arise from the merger of two neutron stars, or a neutron star and a black hole. The energy released in a fraction of a second during a typical gamma-ray burst exceeds the total energy our Sun will produce over its entire 10 billion-year lifetime by several orders of magnitude. A particularly energetic burst releases in milliseconds what our Sun would take hundreds of billions of years to produce. That energy jets outward in tightly focused beams. If either beam happens to point toward Earth, we detect a burst bright enough to be visible to telescopes even at cosmological distances of billions of light years. The boat burst from October 2022 originated about 2 billion light years away and triggered saturation effects in nearly every gamma-ray detector in space. They were designed for energies far lower than what arrived. Despite originating 2 billion light-years distant, it produced measurable ionization effects in Earth's lower ionosphere. Researchers detected disruptions to long-wave radio propagation, the kind used for submarine communications, that lasted for hours after the burst arrived. 2 billion light-years. Ionized Earth's atmosphere from that distance. That's what the dark patches between visible stars are hiding, not emptiness. Violent physics operating at energies and scales so extreme that our intuitions for what's possible don't apply. One specific number crystallizes the entire cosmic darkness story in a way that stays with you. The surface brightness of the entire night sky, the total light arriving from all sources combined, measured across the visible spectrum, works out to roughly the equivalent of a single 50th magnitude star spread uniformly across the whole sky. That's a star about 25 billion times fainter than the faintest object visible to the naked eye, distributed uniformly across all 180,000 square degrees of the celestial sphere. Think about what that means. Every galaxy, every star, every nebula, every active galactic nucleus in the observable universe, all their light combined, arriving at Earth simultaneously, produces a sky that, if that light were spread uniformly rather than coming in distinct points, would glow at a brightness 25 billion times below what your eyes can detect. The universe is full. It's producing light at rates that dwarf any human reference point. And it deposits at Earth a total sky brightness so thin it disappears below the threshold of human vision against a dark background. Distance and expansion win so completely that the output of 2 trillion galaxies, each containing hundreds of billions of stars, produces a sky indistinguishable from complete darkness to any biology that evolved at the bottom of a planetary atmosphere. The history of measuring stellar distances, the observational backbone that makes all of this quantifiable, follows a chain of techniques that each extends the range of the previous one, and the chain itself tells a story about how cumulative science works. The nearest stars can be measured through parallax, the apparent shift in position of a nearby star against distant background stars as Earth moves from one side of its orbit to the other, providing a baseline of about 300 million kilometers. This method works reliably out to a few thousand light-years. The Hipparcos satellite, launched in 1989, measured parallaxes for about 118,000 stars with unprecedented precision. The Gaia mission, launched in 2013 and still operating, extended that to nearly 2 billion stars, creating by far the most precise three-dimensional map of the Milky Way ever constructed. Beyond parallax distances, the next rung involves Cepheid variable stars, stars that pulsate with periods directly related to their intrinsic luminosity. Henrietta Swan Leavitt discovered this relationship in 1912 while working at the Harvard College Observatory, cataloging the brightness of variable stars in the Small Magellanic Cloud. Her discovery allowed astronomers to determine the intrinsic brightness of any Cepheid just by measuring its pulsation period. Compare intrinsic brightness to apparent brightness, accounting for the inverse square law, and distance follows directly. Leavitt's discovery made it possible for Edwin Hubble to establish that the Andromeda galaxy lay far outside the Milky Way and to measure the expansion of the universe. Beyond Cepheids, Type 1a supernovae extend the distance ladder to billions of light-years, the standard candles that revealed dark energy. Each rung of that ladder extends the reach of human observation across a universe that would otherwise remain unmeasured and incomprehensible. Each measurement made a specific piece of the darkness question answerable. Leavitt's patient cataloging in 1912 ultimately led, through a chain of scientific dependencies, to Perlmutter's Nobel Prize in 2011, and to our understanding of why the sky stays dark as the universe accelerates its own expansion. The human visual system has one more quirk relevant to this story that rarely appears in astronomy writing. Dark adaptation, the process by which the eye becomes sensitive to low light levels, takes about 20 to 30 minutes to complete fully. During that process, the pupil dilates, expanding from about 2 millimeters in bright light to about 7 or 8 millimeters in complete darkness. More importantly, the rod cells in the retina undergo a chemical change involving the buildup of rhodopsin, a photosensitive pigment that bleaches when exposed to bright light and regenerates in darkness over those 20 to 30 minutes. A fully dark-adapted eye, with a pupil dilated to 7 millimeters, collects roughly 50 times more light than the same eye in bright conditions. Under ideal conditions, rod cells can detect individual photons. This makes fully dark-adapted human vision one of the most sensitive light detectors in nature, at the wavelengths the eye responds to. And yet, even this extraordinarily sensitive biological instrument can barely detect the sky's total integrated brightness. The combined light of 2 trillion galaxies, arriving at Earth after billions of years of travel, barely registers against the dark-adapted retina as anything other than scattered points against blackness. The individual stars and galaxies you can see on a clear, dark night represent the extreme bright end of a luminosity distribution extending downward by 30 or more orders of magnitude to sources utterly invisible without technology. The darkness isn't a failure of perception. It's an accurate report on what the universe deposited. Here's a thought experiment that takes about 30 seconds and permanently changes how you think about the night sky. Pick any dark patch between 2 visible stars. Not a patch near the Milky Way, somewhere that looks genuinely empty. Hold a grain of sand at arm's length, lined up with that patch. The grain covers a tiny fraction of the sky. Now consider that in 1995, astronomers pointed the Hubble Space Telescope at a patch of sky roughly that size, about 1/30th of the diameter of the full moon, in the constellation Ursa Major. It looked completely empty. No visible stars in that direction. Just dark. They left the camera running for 10 consecutive days. What came back was the Hubble Deep Field, an image containing roughly 3,000 individual galaxies. Not stars, galaxies. Each one containing hundreds of billions of stars. Some of them appearing as they existed barely a billion years after the Big Bang. All of them invisible to the naked eye. All of them invisible to a brief glance through even a large amateur telescope. Revealed only because the photons were given enough time to accumulate into a detectable signal. 3,000 galaxies in a patch of sky you could cover with a grain of sand. Then astronomers did it again in 2004, pointing the advanced camera for surveys on Hubble at a spot in the southern hemisphere for over 400 consecutive orbits, about 11.3 days of cumulative exposure. The Hubble Ultra Deep Field revealed approximately 10,000 galaxies in a region even smaller than the original Deep Field. Some of those galaxies were so distant that their light had been traveling for over 13 billion years. Every dark patch in the sky contains thousands of galaxies invisible to human perception. The darkness isn't emptiness, it's a depth limit. The nature of dark matter adds a specific dimension to the darkness story that goes beyond the 5% accounting of ordinary matter. Dark matter doesn't just fail to emit light. Its gravitational influence actively shapes where visible light exists in the universe. The cosmic web of filaments and voids that large-scale structure surveys reveal the vast network of galaxy clusters connected by threads of galaxies separated by enormous empty voids, follows the skeleton of dark matter distribution laid down in the first fraction of a second after the Big Bang. Dark matter clumped first. Its gravitational potential wells attracted ordinary hydrogen and helium gas, which condensed and eventually formed the first stars in exactly those locations where dark matter had already assembled. The filaments of galaxies you see in large-scale structure maps aren't where galaxies chose to form. They're where dark matter already was. The visible universe is a thin, luminous tracery sketched on top of an invisible scaffold 5 times more massive than everything we can see combined. This means the dark patches in the sky between galaxy filaments, the voids, aren't just low in ordinary matter. They're low in dark matter. The voids represent regions where both the visible and invisible components of the universe thin out simultaneously. The cosmic web glows where the dark skeleton glows gravitationally, and leaves dark gaps where neither visible matter nor dark matter concentrated enough to trigger star formation. Looking into a cosmic void is looking into a region where the universe's dark infrastructure is sparse. The darkness isn't just optical. It runs all the way down to the gravitational foundation. The question of what happens to stellar light inside galaxies before it ever has a chance to escape into intergalactic space deserves more attention than the darkness paradox usually gives it. The interstellar medium inside a typical galaxy like the Milky Way isn't uniformly transparent. Dense molecular clouds, regions where gas and dust concentrate into clumps massive enough to eventually collapse into new stars, can absorb and scatter light so effectively that stars on the far side are completely invisible at optical wavelengths. The center of the Milky Way lies about 26,000 light-years from Earth. In visible light, we can't see it directly at all. 30 magnitudes of visual extinction, a factor of roughly 10 to the 12th in brightness reduction, stand between us and the galactic center. Dust in the spiral arms of our galaxy absorbs essentially all the visible light from the nuclear bulge before it reaches us. Radio waves and infrared penetrate that dust far more effectively. The Very Large Array radio telescope has mapped the galactic center in radio wavelengths in extraordinary detail. The Chandra X-ray Observatory has imaged it in X-rays. Infrared observations have tracked individual stars orbiting within a fraction of a light-year of the central supermassive black hole, Sagittarius A star, revealing its mass of about 4 million solar masses through the precise orbital dynamics of those stars. That work earned Reinhard Genzel and Andrea Ghez the Nobel Prize in Physics in 2020. The visible darkness of the galactic center isn't a cosmic property. It's a local absorption effect. Dust in our own galaxy's disk blocking light that exists and travels freely, just not toward us at visible wavelengths. It's a reminder that the darkness we see depends not just on source distances and cosmic expansion, but on what lies between the sources and our eyes in the immediate neighborhood. Stellar evolution connects to darkness in one more way that rarely gets discussed in this context. Stars don't maintain constant luminosity throughout their lives. Our Sun, currently about 4.6 billion years old and roughly halfway through its main sequence lifetime, shines at about 3.8 times 10 to the 26th watts. But it wasn't always this luminous. When it first ignited about 4.6 billion years ago, it was only about 70% as bright as it is today. Over billions of years, as hydrogen fuses to helium in the core, and the helium ash gradually increases the core's mean molecular weight, the core contracts slightly, temperatures rise, and luminosity increases slowly and steadily. This gradual brightening, common to all main sequence stars, means that the early universe, when only the first generations of stars existed, was genuinely dimmer than the present-day universe in terms of total luminosity per unit volume. The universe has been brightening over its history as stellar generations have accumulated. It's currently near a kind of peak activity in terms of star formation rate, having declined from an earlier peak around 10 billion years ago, when the cosmic star formation rate was roughly 10 times higher than today, but still burning through its remaining hydrogen reserves in billions of active galaxies. The darkness we see tonight is the darkness of a universe that has been getting brighter for billions of years and will eventually, as stars die faster than new ones form, grow darker again, this time permanently. Number counts, the actual counting of how many galaxies exist per unit area of sky, offer the most direct quantitative bridge between cosmic inventory and the darkness paradox. Deep survey programs like the Cosmic Evolution Survey, the Great Observatory's Origins Deep Survey, and the Sloan Digital Sky Survey have counted galaxies systematically across large areas of sky to various depth limits. Combining those counts and extrapolating to the entire sky, the best current estimates suggest the observable universe contains somewhere between 100 billion and 2 trillion galaxies. The higher estimate, published by Christopher Consellis and colleagues from the University of Nottingham in 2016 in the Astrophysical Journal, came from a careful analysis of galaxy number density across different epochs of cosmic history, concluding that most galaxies at high redshift are too small and faint for current instruments to detect, meaning previous estimates dramatically undercounted them. 2 trillion galaxies, average of perhaps 100 billion stars each, total of around 200 sextillion stars, 2 times 10 to the 23rd power, in the observable universe alone. If you distributed those stars uniformly across the surface of a sphere with the radius of the observable universe and asked what fraction of the sky they covered, accounting for their physical sizes and the inverse square law, the answer comes out to approximately 10 to the minus 23. That's the fractional coverage of the sky by stellar surfaces. 1, followed by 22 zeros, in the denominator. Most lines of sight from Earth pass through 22 orders of magnitude of empty space before reaching a stellar surface. Or, in the case of most lines of sight, they don't reach one at all, within the observable universe. They extend to the cosmological horizon and arrive as ancient, stretched, invisible microwave radiation rather than visible starlight. The discovery of exoplanets, planets orbiting other stars, adds a dimension to the darkness question that didn't exist as a scientific reality until relatively recently. Before 1995, the existence of planets beyond our solar system was theoretical. The first confirmed detection of an exoplanet orbiting a sun-like star came in October 1995, when Michel Mayor and Didier Queloz of the University of Geneva announced the discovery of a planet orbiting the star 51 Pegasi, about 50 light-years from Earth. The planet, named 51 Pegasi b, now informally called Dimidium, orbited its host star in just 4.23 days, extraordinarily close to the stellar surface. Mayor and Queloz received the Nobel Prize in Physics in 2019 for that discovery. Since then, the Kepler Space Telescope, launched in 2009, has confirmed the existence of more than 2,700 exoplanets. The TESS satellite, launched in 2018 and still operating, has identified thousands more. Current estimates suggest that essentially every star in the Milky Way hosts at least one planet on average. Some stars host multiple planetary systems. The galaxy contains hundreds of billions of planets. What does this mean for darkness? It means the dark points of light you see in the night sky aren't just stars. They're stellar systems with planetary retinues. Somewhere in those systems, some fraction of those planets may orbit in the habitable zone, the range of distances where liquid water can exist on a planetary surface under appropriate atmospheric conditions. Some subset of those may have actually developed life. Some smaller subset may have developed technological civilizations. None of those hypothetical civilizations have made themselves visible to us. The night sky remains dark in the radio bands, dark in the optical bands, dark in every band we've monitored for signals suggesting intelligence. The SETI program has been running for over 60 years without a confirmed detection. Either we're alone, or life is rare, or civilizations don't broadcast, or something else eliminates them before they can make themselves visible across interstellar distances. The darkness of the sky contains not just the answer to Olber's paradox. It may contain the answer to the Fermi paradox too. And those two answers may be related in ways we haven't fully worked out yet. The timescale problem in astronomy deserves its own meditation, because it reshapes everything about how the night sky should be understood. Human civilization has existed for perhaps 10,000 years in any meaningful sense. Writing, cities, organized knowledge, 10,000 years at most. Modern scientific astronomy, with instruments capable of measuring stellar distances, cosmic expansion, and the composition of distant galaxies, at most 400 years. And the really transformative measurements happened in the last 100. The light you see from the Andromeda galaxy tonight left that galaxy 2.5 million years ago. When that light departed, Homo sapiens didn't yet exist as a species. The genus Homo was just beginning to walk upright on African savannas. Whatever that photon passed through, whatever it narrowly missed, whatever gravitational lenses slightly bent its path over 2.5 million years of travel, all of that history is embedded in its arrival at your retina tonight. Some of the brightest stars in the night sky are so far away that the light entering your eye left them before modern humans arrived. Eta Carina, one of the most luminous stars in the Milky Way and a candidate for an imminent supernova, sits about 7,500 light-years away. The light you see from it tonight left about 7,500 years before now, when human civilization was just developing writing, when Egypt's old kingdom hadn't yet built the pyramids. The star we see tonight might already have exploded. We won't know for another 7,500 years. The sky isn't a picture of the universe as it exists. It's a composite exposure across different moments in cosmic time, layered together into a single view. Nearby stars show their recent history. Distant galaxies show their ancient history. The cosmic microwave background shows a moment before any of those structures existed. Looking at the night sky means seeing multiple epochs simultaneously, collapsed into one experience. The fate of the Milky Way offers the most personal version of the darkness story, because it directly affects what the sky will look like from Earth, if Earth still exists, in the very long run. The Milky Way and the Andromeda galaxy are currently approaching each other at roughly 110 kilometers per second. In about 4.5 billion years, the two galaxies will begin a complex gravitational interaction. Not a violent collision in the everyday sense, since the vast distances between individual stars make actual stellar collisions extraordinarily rare, but a reshaping of both galaxies' structures through tidal forces. Over the following few billion years, the two galaxies will merge into a single elliptical galaxy, sometimes called Milkdromeda in popular discussions. During the merger, the night sky from any surviving planetary system within either galaxy would look nothing like it does tonight. Star formation, triggered by gas compression during the interaction, would temporarily light up both galaxies with newly born massive stars. The night sky would blaze with hundreds of times more visible stars than the current Milky Way disk provides. New, bright star-forming regions, luminous young star clusters, the combined structural chaos of two merging spiral galaxies, all of it compressed into one spectacular overhead display. Then, it would fade. The merger uses up gas. Star formation slows. The new elliptical galaxy settles into a quieter existence. Over tens of billions of years, its remaining stars age and die. The sky darkens progressively. Eventually, by the time cosmic expansion has carried all other galaxies beyond the cosmological horizon, the merged remnant contains only cooling white dwarfs, neutron stars, and black holes, with occasional flickers as two remnants collide, or a white dwarf accretes enough mass to detonate as a Type 1a supernova. The sky ends dark, not as a starting condition, but as an endpoint. The darkness Olber's worried about isn't the natural state of a universe full of stars. It's the destination. There's one final physical reality that ties every strand of this story together, and it's elegant in the way that only deeply true things tend to be. The same finite speed of light that creates the observable universe's horizon, the boundary beyond which we cannot see, also means that every observation we make looks backward in time. There's no such thing as seeing the universe as it currently exists. Everything we observe as it was, with the delay determined by the distance. The nearby stars show us years-old light. Distant galaxies show us billions of years-old light. The cosmic microwave background shows us a universe that no longer exists in that form anywhere in space. This makes the night sky the most direct time machine available to human senses. Looking at a faint galaxy cluster through a large telescope isn't just seeing far away, it's seeing billions of years into the past, observing the universe at an epoch before our sun existed, before the solar system formed, before any of the carbon in your body had been synthesized inside a stellar interior. The darkness between those clusters is the absence of light that hasn't arrived yet, future light from the universe's present state, which will reach Earth in billions of years. The darkness isn't a void, it's a calendar. It marks the difference between how old the universe is and how far light has traveled in that time. And that calendar keeps running. Every year, a thin shell of previously unreachable space becomes observable as light from slightly more distant sources arrives for the first time. The observable universe expands by 1 light-year every year, slowly, relentlessly, adding new territory to the portion of the cosmos that can speak to us. Not fast enough to overcome the recession of galaxies beyond the cosmological horizon, but real nonetheless. The night sky will never be fully dark, because the universe never stops producing light. And it will never be fully bright, because the universe is too large and too young and too actively expanding for all that light to arrive simultaneously at any given point. It will be exactly what it is tonight, mostly dark, scattered with points, carrying messages from every epoch of cosmic history layered on top of each other, with the darkness itself being the most informative signal of all. There's a specific moment in the history of the universe when the darkness question became answerable. And it happened not in a university observatory or at a physics conference, but in a patch of New Jersey scrubland, in a converted horn antenna originally built for satellite communications, during an attempt to eliminate a source of interference that turned out to be the most important signal in the history of cosmology. Arno Penzias and Robert Wilson weren't looking for the Big Bang. They were trying to do radio astronomy, mapping faint microwave emissions from the Milky Way. Their instrument, a large horn reflector antenna at the Bell Labs facility in Homedale, New Jersey, kept picking up a steady hiss of microwave noise coming from every direction in the sky. It didn't vary with the time of day. It didn't vary with the season. It didn't correlate with any known terrestrial source of interference. It came equally from every direction simultaneously, with a temperature corresponding to about 3.5 degrees above absolute zero, close to but slightly higher than what would eventually be measured as the true value. They did everything right. They checked the electronics. They looked for sources of spurious emission. They found a pair of pigeons nesting inside the horn and removed them, along with what they diplomatically called white dielectric material in the published paper, pigeon droppings. They cooled parts of the receiver to minimize thermal noise contributions. The signal remained. Meanwhile, about 50 kilometers away at Princeton University, a team led by Robert Dickey was constructing an instrument specifically designed to search for exactly the signal Penzias and Wilson had already found. Dick and his colleagues, Jim Peebles, Peter Roll, and David Wilkinson, had worked out the theoretical prediction from first principles. If the Big Bang model were correct, a residual thermal radiation from the hot early universe should permeate all of space, cooled by cosmic expansion to just a few degrees above absolute zero. When Penzias called Dick to describe the unexplained signal, Dick reportedly hung up the phone and said to his team, "Boys, we've been scooped." Penzias and Wilson published their measurement in the Astrophysical Journal in 1965. Dick and colleagues published the theoretical interpretation in the same issue. Together, the two papers established the cosmic microwave background as an observational reality, and by doing so, closed the last major escape route for steady-state models of the universe and confirmed that the cosmos had a hot, dense beginning. Penzias and Wilson received the Nobel Prize in Physics in 1978. Dick, Peebles, Roll, and Wilkinson did not share it, despite providing the theoretical framework that explained the discovery. Jim Peebles did eventually receive the Nobel Prize in Physics in 2019, awarded partly for his fundamental theoretical contributions to cosmology, but 54 years after the discovery he helped interpret. The background radiation those researchers confirmed explains a specific feature of the darkness that becomes visible only when you think carefully about what complete darkness would actually feel like in an otherwise empty universe. Even intergalactic space, the vast voids between galaxy clusters, isn't cold in an absolute sense. It maintains a temperature of 2.725 degrees Kelvin, above absolute zero, set by the energy density of the cosmic microwave background, filling it uniformly. There's no location in the observable universe where you could cool an object below that temperature, because the CMB photons hitting it from every direction would always maintain it at that minimum. The coldest possible temperature anywhere in the observable universe is 2.725 Kelvin. The darkness of intergalactic space is a darkness with a flaw. The question of what counts as a star, and therefore what counts as a source of light, turns out to be more complicated than casual descriptions suggest, and the complications matter for the darkness accounting. Brown dwarfs sit below the mass threshold for sustained hydrogen fusion, roughly 80 Jupiter masses, or about 8% of a solar mass. Objects below that threshold never ignite as stars in the conventional sense. They may fuse deuterium briefly when young, and the most massive of them may fuse lithium for a period, but they never achieve the sustained proton-proton chain reactions that power main sequence stars. They glow faintly in infrared from gravitational contraction and residual heat, gradually cooling over billions of years. Current estimates suggest brown dwarfs may be nearly as numerous as true stars in the galaxy. Some surveys suggest a ratio close to 1 brown dwarf per 2 main sequence stars. But their contribution to total galactic luminosity is negligible. They're essentially invisible compared to even the dimmest red dwarf stars. Red dwarf stars, M-type main sequence stars with masses between about 8% and about 50% of a solar mass, represent by far the most numerous class of true stars. Roughly 70% of all stars in the Milky Way are red dwarfs. They burn so slowly and so efficiently that their lifetimes extend to tens or even hundreds of billions of years, longer than the current age of the universe. No red dwarf star that formed when the first galaxies appeared has yet died. Every red dwarf that has ever formed still exists. Despite their numbers and their longevity, red dwarfs contribute relatively little to the visual sky. Their surface temperatures range from about 2,400 to about 3,700 Kelvin, making them dim, reddish objects that emit most of their energy in near-infrared wavelengths rather than visible light. The dimmest red dwarfs produce less than 1/10,000th of the Sun's luminosity. Even Proxima Centauri, the nearest star to our Sun at 4.24 light-years, a red dwarf, has an apparent magnitude of about 11, far too faint to see without a telescope despite being our nearest stellar neighbor. This means the vast majority of stars in the universe contribute almost nothing to the visible darkness paradox. They exist, they emit, but their light falls below both the visible wavelength range and the flux threshold detectable by unaided human vision. The night sky you see overhead reflects primarily the contribution of giant stars, massive hot blue stars, and intermediate mass stars like our Sun. A luminosity-biased sample that represents a small fraction of the actual stellar population. The spectrum of starlight itself carries embedded information that took over a century to fully decode, and that information reshaped our understanding of what stars are and what the darkness between them means. In 1814, the German optician Joseph von Fraunhofer passed sunlight through a narrow slit and a prism, producing a spectrum, a rainbow of colors spread out in order of wavelength. He noticed dark lines crossing the spectrum at specific wavelengths. Not smears, not gradients, precise, narrow, dark lines at exact positions corresponding to specific colors. He catalogued hundreds of them and labeled the most prominent with letters: the D lines in yellow, the G line in blue-green, the H and K lines in violet. Fraunhofer didn't know what those lines meant. The interpretation came decades later. Each dark line corresponds to a specific chemical element absorbing light at a characteristic wavelength as sunlight passes through the Sun's cooler outer atmosphere. Sodium absorbs at the D lines, calcium at H and K, hydrogen at a series of lines throughout the visible spectrum, the Balmer series, with the most prominent at 656.3 nanometers in the red, called H-alpha. This means every star's spectrum contains a chemical fingerprint. By carefully measuring the wavelengths of absorption lines in stellar spectra, astronomers can determine what elements a star contains, what its surface temperature is, and, crucially for the darkness question, how fast it's moving toward or away from us. A star moving away shows absorption lines shifted toward longer, redder wavelengths. Moving toward us, the lines shift toward shorter, bluer wavelengths. The magnitude of that shift, compared to the known rest wavelengths of those lines, gives velocity directly through the Doppler formula. This is precisely how Hubble measured galaxy recession velocities in the 1920s. Not by watching galaxies move, the motion is far too slow to detect over a human lifetime, but by measuring the redshift of absorption lines in the combined spectra of billions of stars making up each galaxy. The entire edifice of cosmic expansion, the Hubble constant, the age of the universe, the explanation of cosmic darkness, all of it traces back to Fraunhofer's careful observation of dark lines crossing a rainbow in Munich in 1814. The actual counting of stellar ages provides one of the cleanest independent confirmations that the universe has a finite age, and therefore a finite supply of available photons. Stars consume hydrogen at rates that depend sensitively on their mass. More massive stars burn hotter and faster through a process called the CNO cycle, rather than the slower proton-proton chain that dominates in lower mass stars like our Sun. A star 10 times the mass of our Sun burns through its hydrogen fuel roughly 10,000 times faster than the Sun does, despite having only 10 times as much of it, making its lifetime roughly 1,000 times shorter. The most massive stars, with masses of 100 solar masses or more, last only a few million years before exhausting their cores and exploding as supernovae. This means massive, luminous stars visible in the night sky, the blue-white giants and supergiants that dominate the sky's brightness at visible wavelengths, are by definition young. Rigel in Orion, one of the most luminous stars visible to the naked eye at roughly 120,000 solar luminosities, has an estimated age of only about 8 million years. The entire dinosaur era lasted longer than Rigel has existed as a star. When Rigel exhausts its fuel and explodes, the resulting supernova will briefly outshine every other star in the Milky Way, visible in daylight from Earth. The presence of such stars in the current universe confirms that star formation has continued throughout cosmic history. These are not leftover stars from the Big Bang. They're newly minted, cosmically speaking. But their short lifetimes also mean they're evidence of ongoing stellar birth and death, a cycle that depends on the continuing availability of hydrogen gas, and that will eventually cease when that gas supply is exhausted. Globular clusters, dense spherical collections of hundreds of thousands of stars orbiting the outer halo of the Milky Way, provide the clearest direct measurement of stellar ages. The stars in a globular cluster all formed at approximately the same time from the same gas cloud. By mapping their positions on a Hertzsprung-Russell diagram, a plot of luminosity versus surface temperature, astronomers can identify the point at which stars are just leaving the main sequence and beginning to evolve into red giants. That point, called the main sequence turnoff, occurs at a luminosity and temperature that depends directly on age. The oldest globular clusters in the Milky Way have turnoff points corresponding to ages of 12 to 13 billion years, consistent with, but slightly younger than, the 13.8 billion year age of the universe. Exactly as expected if those clusters formed within the first billion years after the Big Bang. Light pollution deserves a more careful technical treatment than it usually receives in discussions of cosmic darkness, because the physics of how artificial light brightens the sky tells you something specific about the natural darkness being destroyed. Natural sky background at a dark site far from any city comes from several sources. Airglow, faint chemiluminescence from molecules in the upper atmosphere excited by solar ultraviolet radiation during the day and releasing energy at night, contributes a diffuse glow at specific wavelengths, primarily in the green and red parts of the spectrum. Zodiacal light. Sunlight reflected off interplanetary dust particles concentrated in the plane of the solar system produces a faint glow along the ecliptic, most visible as a cone of light rising from the horizon after sunset or before sunrise under ideal conditions. Scattered starlight from the Milky Way itself and the integrated light of unresolved distant galaxies contribute additional background. All of these natural sources combined produce a sky background at the darkest accessible sites, places like the Atacama Desert in northern Chile, Mauna Kea in Hawaii, or certain sites in the Canary Islands, of about 22 magnitudes per square arcsecond. That's the standard unit for sky brightness in astronomy. At that level, the Milky Way is brilliant. Thousands of stars are visible to the naked eye, and faint galaxy clusters glow visibly through modest telescopes. Artificial light scatters off molecules and aerosols in the lower atmosphere and arrives at the observer from directions other than the actual light sources. Even a moderately sized city 100 kilometers away elevates the sky brightness by a detectable amount. In a large metropolitan area, the sky brightness might reach 17 or 18 magnitudes per square arcsecond, roughly 25 to 60 times brighter than a natural dark sky, washing out everything but the brightest stars and planets. The quantity that astronomers care about, the darkness available for detecting faint objects, scales dramatically with sky background. At a sky background 25 times brighter than natural, a telescope must observe 25 times longer to achieve the same signal-to-noise ratio on a faint target. For objects right at the detection limit, a telescope at a light-polluted site may simply never accumulate enough signal to detect them, regardless of how long it observes. The light from the city fills the detector continuously, masking the faint photons from the universe. This is why the world's major observatories sit in remote, high-altitude, arid locations, not primarily for atmospheric clarity, though that matters, but to maximize access to the natural darkness that the physics of the universe provides, and that the physics of scattered artificial light progressively destroys. The relationship between darkness and the detection of gravitational waves, a different kind of cosmic signal entirely, reveals how the night sky story extends beyond photons. When the LIGO detectors made the first confirmed observation of gravitational waves on September 14, 2015, detecting the merger of two black holes roughly 1.3 billion light-years away, they opened an entirely new observational window on the universe. Not electromagnetic radiation, not photons at any wavelength. Physical distortions of space-time itself. Ripples propagating at the speed of light, stretching and compressing the fabric of space as they passed through Earth. The signal, designated GW150914, lasted about 0.2 of a second in the detectable frequency range. The black holes involved had masses of approximately 36 and 29 solar masses, respectively, merging into a final black hole of about 62 solar masses. The missing 3 solar masses were radiated as gravitational waves in that fraction of a second, an energy release equivalent to roughly 50 times the total luminosity of the entire observable universe in electromagnetic radiation, but in gravitational waves rather than light. That energy was invisible. No photon, no gamma ray, no radio emission. Pure gravitational radiation, interacting so weakly with matter that it passed through Earth without depositing any measurable energy. The entire event happened in darkness, in every electromagnetic sense of the word. It was detectable only through the 4-kilometer arm-length interferometers of the LIGO observatories, sensitive enough to detect a change in length of about 1/10,000th the diameter of a proton. Gravitational wave astronomy has since catalogued over 90 confirmed events: black hole mergers, neutron-star mergers, and potentially mixed events involving objects of uncertain classification. Each one happened in complete electromagnetic darkness. The sky of gravitational wave sources doesn't overlap with the sky of photon sources in any simple way. Black hole mergers, now known to be common events throughout the universe, produce no light at all under most circumstances. They've been happening since the first black holes formed, filling the universe with gravitational signals that passed through every obstacle undetected until September 2015. The darkness hides more than redshifted light from distant galaxies. It hides an entirely parallel universe of gravitational wave events that have been occurring for billions of years, completely invisible to any electromagnetic detector. The search for the universe's first light, the radiation from the very first stars, represents one of the most active frontiers in observational astronomy, and the technical challenge involved illuminates exactly how extreme the darkness problem becomes at the edge of the observable universe. The first stars, population 3 stars, formed from primordial hydrogen and helium gas sometime between about 100 million and 400 million years after the Big Bang. No direct observation of these stars has yet been achieved. Their light has been traveling for over 13 billion years, redshifted from ultraviolet or optical wavelengths at emission into infrared wavelengths reaching Earth today. The infrared background, the diffuse glow of unresolved sources in the infrared sky, should contain their contribution, but separating it from the vastly brighter foreground of nearby sources, zodiacal light, and instrumental backgrounds requires extreme precision. The James Webb Space Telescope's primary design goal includes detecting light from galaxies existing just a few 100 million years after the Big Bang, the immediate descendants of population 3 star formation, if not the population 3 stars themselves. Webb's 18.5-meter equivalent primary mirror, operating primarily in the near and mid-infrared between approximately 0.6 of a micron and 28 microns, provides the combination of collecting area and wavelength coverage needed to detect the redshifted ultraviolet and optical light of these ancient sources. Early Webb results, published in 2022 and 2023, have revealed galaxies at redshifts above 12, meaning we see them as they appeared when the universe was less than 4% of its current age, roughly 400 to 500 million years after the Big Bang. Some of these galaxies appear to contain more stellar mass than models predicted would exist so early, prompting revisions to our understanding of how rapidly galaxies assembled in the early universe. The light from those galaxies has been traveling for over 13 billion years. It arrived at Webb's mirror carrying information about stellar populations, star formation rates, chemical abundances, and galaxy structure at an epoch when the Milky Way itself had barely begun to form. Reading that information from photons weakened by 13 billion years of cosmic expansion and stretched from ultraviolet into near-infrared is one of the most technically demanding observational challenges humans have ever attempted. The darkness at the edge of the observable universe isn't absolute. It's information, encoded in photons so faint and so stretched that detecting them required building the most sensitive infrared telescope in history and launching it to a stable orbit 1.5 million kilometers from Earth at the second Lagrange point, a location chosen precisely because it keeps the telescope permanently shielded from the Sun, Earth, and Moon simultaneously, maximizing sensitivity to the faintest signals the universe sends. One final observation brings this entire exploration back to something personal and immediate. The photons entering your eye when you look at a dark night sky have had extraordinary journeys. The ones from nearby stars have been traveling for years. The ones from the Andromeda galaxy smudge, if you can find it, for 2.5 million years. The ones from the faintest galaxy you could possibly detect through a large amateur telescope have been traveling for hundreds of millions of years, leaving their source before complex animal life existed on Earth. But the vast majority of photons that hit your retina when you look at the night sky don't come from stars or galaxies at all. They come from the cosmic microwave background, the 1,000 per square centimeter per second we mentioned earlier, and from airglow, zodiacal light, and the integrated flux of unresolved sources. Your eye can't detect any of these. They fall below the threshold of visual sensitivity or outside the visible wavelength range entirely. What you actually see when you look at the night sky is the extreme luminous tail of a distribution extending downward by many orders of magnitude into invisibility. The visible stars represent the loudest voices in a chorus so vast that even with the most sensitive instruments ever built, we still hear only a fraction of the singers. The darkness between the stars holds more information than the stars themselves. It encodes the age of the universe in the horizon it establishes. It encodes the rate of expansion in the degree to which ancient light has been stretched and dimmed. It encodes the geometry of space in the angular scales of temperature fluctuations in the microwave background. It encodes the existence of dark matter in the distribution of galaxies across the cosmic web. It encodes the presence of dark energy in the accelerating recession of the most distant visible sources. Every square degree of dark sky is a measurement. The universe has been making that measurement continuously for 13.8 billion years. We've only been reading it for about 100. A few final observations before the honest accounting. The history of Olbers' paradox tracks almost exactly with the history of humanity learning to ask better questions. Every proposed solution that failed, interstellar dust, a finite boundary of stars, tired light, failed not because the people proposing it were careless, but because the question turned out to be deeper than it appeared. Each failed answer forced a sharper reformulation of what was actually being asked. By the time the correct answer arrived, assembled from Hubble's expansion measurements, the cosmic microwave background discovery, the detailed surveys of galaxy counts, the detection of dark energy, it required dismantling the assumption that the universe has no history. The darkness of the sky depends entirely on the universe having begun. That's an unusual situation in science. Most questions about nature don't carry such direct implications about origins. The darkness of the night sky isn't just an astronomical observation. It's evidence, available to every person who has ever stood outside after dark, that the universe we inhabit had a specific beginning, a finite time ago. that it has been expanding and cooling ever since, and that most of what it contains will never be directly visible to any observer inside it, regardless of the sophistication of their instruments. Here is an honest accounting of what we know, what remains debated, and what current understanding cannot resolve. Firmly established by multiple independent lines of evidence is the following. The observable universe had a beginning, approximately 13.8 billion years ago, confirmed through the Hubble expansion rate, the detailed temperature fluctuations of the cosmic microwave background, and the ages of the oldest globular cluster stars. Space has been expanding continuously since that beginning, carrying galaxies apart and stretching photon wavelengths in proportion to the scale factor of expansion, the process that shifts ancient light out of the visible spectrum and reduces its energy per photon. The cosmic microwave background radiation, discovered in 1965 by Penzias and Wilson and mapped with extraordinary precision by the COBE, WMAP, and Planck satellites, fills all of space uniformly at a temperature of 2.725 Kelvin, confirming that the early universe passed through a hot, dense, opaque phase before becoming transparent at about 380,000 years of age. The observable universe contains between 100 billion and 2 trillion galaxies, each containing hundreds of billions to trillions of stars. But those stars cover only an infinitesimal fraction of the sky, roughly 10 to the minus 23rd of its area, because the distances between stars dwarf their physical sizes by many orders of magnitude. Dark energy, comprising approximately 68% of the universe's energy content, drives accelerating expansion, confirmed by Type 1a supernova distance measurements. Dark matter, comprising approximately 27% of the universe's energy content, shapes the large-scale distribution of visible matter but contributes no light of any wavelength. Together, dark energy and dark matter account for 95% of everything the universe contains, none of which contributes to the sky's brightness under any circumstances. The cosmological event horizon currently sits at roughly 16 billion light-years, beyond which recession velocities exceed the speed of light, and future photons from those sources will never arrive at Earth, regardless of how long we wait. Actively debated and unresolved is the following. The precise value of the Hubble constant, the Hubble tension between measurements derived from the early universe through CMB analysis, giving approximately 67 kilometers per second per megaparsec, and measurements derived from the local universe through Cepheid variables and Type 1a supernovae, giving approximately 73 kilometers per second per megaparsec, remains unexplained and may indicate systematic errors in one or both measurement chains, or may reflect new physics not captured in the standard cosmological model. The total number of galaxies in the observable universe remains uncertain by a factor of roughly 20, depending on assumptions about the abundance of faint, low-mass galaxies at high redshift that current instruments cannot directly resolve. The nature of dark energy, whether it represents a true cosmological constant, as Einstein's equations allow, a dynamical field that evolves over time, or something else entirely, cannot be determined from current observations. Recent DESI results hint at possible evolution in dark energy's properties, but the statistical significance as of 2024 is insufficient for firm conclusions. The question of whether the universe is spatially finite or infinite in total extent remains observationally undecidable with any currently foreseeable instrument, since information beyond the cosmological horizon is permanently inaccessible. The nature of dark matter at the particle level, whether it consists of weakly interacting massive particles, axions, primordial black holes, or something not yet theorized, remains unresolved despite decades of direct detection attempts. Genuinely beyond current reach is the following. What, if anything, preceded the Big Bang, and whether that question is even physically meaningful given that time itself may have begun at or near that event. Whether the universe beyond our cosmological horizon resembles the observable portion, and in particular, whether inflation produced a uniform, large-scale structure, or wildly varying physical conditions in different regions. Whether the cosmological constant has always had its current value, or changed during the universe's history, and if so, what determined its value at each epoch. Whether the darkness of the night sky reflects fundamental properties of a unique universe or a specific combination of parameters that varies across an ensemble of universes, each with different physical laws and constants. Whether any civilization has ever, or will ever, directly observe the transition from the cosmic dark ages to the era of first light. A measurement that would require detecting individual population 3 stars or their immediate successors, a goal current instruments approach but have not yet achieved. The night sky is dark. It was always going to be dark, given the physics that govern this universe. The finite age of the cosmos, the expansion of space, the stretching of photon wavelengths across billions of light years of travel, the vast ratio of empty space to stellar surfaces, and the fundamental invisibility of the dark matter and dark energy that together constitute most of existence. All of these converged to produce a sky that looks mostly black to a biological organism standing on a rocky planet at this particular moment in cosmic history. Every proposed alternative, a universe old enough, large enough, and static enough for every line of sight to terminate on a stellar surface, would have made life impossible. Temperatures everywhere at thousands of degrees, no stable chemistry, no liquid water, no biology of any description we could recognize. The darkness you see above you tonight is, among other things, evidence that the universe is compatible with your existence. None of this was obvious for 300 years. The answer required the invention of spectroscopy, of large reflecting telescopes, of radio receivers sensitive enough to detect thermal noise at 3 degrees above absolute zero, of orbiting observatories above the atmosphere, of interferometric gravitational wave detectors sensitive to distortions smaller than a proton's diameter. It required Heinrich Olber's clear formulation of the paradox in 1823, Henrietta Swan Leavitt's discovery of the Cepheid period luminosity relation in 1912, Edwin Hubble's measurement of cosmic expansion in 1929, the accidental detection of the CMB by Penzias and Wilson in 1965, and the discovery of dark energy by Perlmutter, Schmidt, and Rees in 1998. Every clear night sky you will ever see contains all of that history, compressed into the simple observation that it is dark and mostly empty between the scattered points of light. The answer to why has taken humanity 3 centuries, dozens of Nobel Prizes, and instruments costing billions of dollars to assemble fully. The question took one curious mind looking up and noticing that something obvious seemed wrong.